This is the last topic for A1 physics regarding particle physics, nuclear physics, atomic physics, whatever you like to call this. This is up to you. So, of course, before we start with the lesson, we assume in this chapter that the basics of O levels at least are, you are familiar with these basics before starting with this chapter. So if you feel that this lesson or this class feels a bit rushed, that means that your O levels basics are weak. I will attach the link of O levels basics, or at least the link of that playlist in the description of this video. But if you are familiar with those, if that chapter is very strong in your knowledge, then this chapter will not be a difficult thing to do, but at least carry forward. So first, according to the syllabus, we have to go through the alpha scattering experiment, which is again taken from O levels. What was the main idea behind alpha scattering experiment? They were trying to find out what the atom or the nucleus looks like. What are the basic structure of the nucleus or the atom at the time? So there were a few observations based on what they did in the experiment. And based on those observations, we have some conclusions on how the atom may look like to us. And I will show you an animation for that as well. But first we need to see what the observations were. So the observation was that we had an alpha source introduced. Now alpha is positively charged helium nucleus. You can say that alpha has an atomic notation of 4-2, which means it has 2 protons and 2 neutrons inside the nucleus. It is stripped off of its electrons, so it's just the nucleus being bombarded towards this gold foil. Now, what was seen is that there were many particles that were non-deflected. Non-deflected means that they were not deviating from their main path. So approximately in terms of O levels or IGCSE, we say that approximately all of them, or 99% of them, actually pass straight through without any deflection. A very few of them, approximately less than 1%, showed up at angles around 45 degrees, right, 250 degrees, or somewhat in the same zone, right? Okay, so, and a very, very rare chance, less than 0.001% of the times, we saw particles actually flying off towards the gold foil, but not being able to pass through. They actually came back, or you can say that they were deflected at large angles, or larger than 90 degrees at least, at which the gold foil was placed. Now, the rest of these observations were still acceptable, but this was not. This is what they were not okay with. You can say that they were baffled by this observation. That how is this possible? It looks like that if you throw a ball towards a wall and it bounces back, okay, fine. But if that is the case, then how is it penetrating through the wall? So if they accepted this observation, then this became wrong. And if they accepted this one, then these became wrong. So what was the atomic model that they actually came up with? That what does it look like? So they came up with this model that the nucleus is at the center and all the alpha particles are actually passing straight through them, and a very few particles which actually have the liberty or by chance come in front of this nucleus are actually being deflected away, because the nucleus is also positively charged and the alpha was also positively charged. But at the time, we need to accept this. We need to respect this idea that they didn't know this. They only saw this deflection. And based on this idea, they draw the conclusion that something over there, something in the center, is also positively charged or has the same charge as the alpha particle. And every now and then, with an off chance of less than 0.001%, a few alpha particle or just one alpha particle came forward, or right in front of the nucleus, that it actually couldn't be deflected over here, or over here it actually came back, which gave us the idea that nucleus is, of course, positively charged, which was also confirmed by this deflection, but that the mass of the nucleus is concentrated at the center. So what were the ideas, or what were the observations? So first, most of the particles were passing straight through. So this was the observation, right? And this was the conclusion. What did they take out of that? So what was the conclusion they made? What was the idea? That atom is mostly empty space. It's empty. Second, some particles which deflected at angles close to 90 or less than 90 or somewhat there, that told us, or that shows us, the nucleus is positively charged. This is actually an answer for the MCQ. The third observation, that particles actually came back, the blue one, gave us the guarantee that nucleus contains most of the mass of the atom. So for example, if we were to measure the mass of the atom with the electrons and with the nucleus, let's say if this is 1 kg, and if we take out this electron by ionization energy or providing ionization energy and just measure the weight of the nucleus or the mass of the nucleus, this will come out as 0.99999 infinite 99 kgs, which means that this is approximately still equal to 1 kg, meaning that nucleus is the cause of mass, not the electrons. Okay. All right. So let's see the animation, what this actually looks like in reality. Okay, so let's see how this is at the center. This is the alpha part. This is the gold foil nucleus, and we're going to introduce alpha particles into this. So let's start projecting alpha particles. Look at the traces, how they are behaving and how they are responding. So just at this moment, okay, let's run this application for a while. So just at this moment, the particles who actually came right in front of the nucleus actually came back. They had no other choice. If you can observe them, you can see that they actually tried to pass through, but they were unable to do so. So they actually had to go back to this side. If I let this run for a while, you can see that afterwards. And the particles who were actually a bit on the side were actually still deflected. Why? Because the alpha is also positive and the nucleus is also positive, right? So these are the observations that they were doing at the time, or they were actually having at the time, right? And notice that rest of the particles are actually happy to go straight forward, no issues at all. Now this animation shows just the behavior with one atom. We are going to also see what happens when all of the atoms are involved, or at least when most of them are involved. Let's see what happens then. Let's run this for a while and see what happens, so you can visualize it properly. Now let's run this for an atomic model. So let's say that we still have the gold nucleus at the center, but now we are actually looking at many atoms rather than just looking at one. So this is a gold atom, this is a gold atom, this is also a gold atom, so on and so forth. And we can see that there are multiple layers of gold atoms stacked on top of one another, right? And let's see what happens when the alpha particle tried to go through them. Let's see what happens now. Okay. You can pick out any atom and just try to observe what's happening with it, what's happening to its trace. Just look at just one of them and try to observe this and try to save this into your mind, so that whenever this question comes into your syllabus or examination, we can easily answer this question. Or you can just keep on repeating, or keep on going back to the same animation, trying to see what is happening with the alpha particle when it tries to go through gold foil. They're all being deflected. Whoever tries to get close to the nucleus gets deflected. And if by any off chance they come exactly in front of the nucleus, they are sent back. All right, so hope we understand this animation now. So these are the first, you can say, first point of the syllabus, in which it says that we need to understand the alpha scattering experiment. So we understand what is the alpha scattering experiment and what it says about the size of the nucleus and the charge of the nucleus. Then he says it describes a simple model of protons and nucleus. And by chemistry, of course, we understand that a nucleus contains protons and neutrons, and the electrons are on the outer side. We understand that. So we understand point number 2. Point number 3 is distinguish between nucleon number and proton number. And now when we write down the name of an element, for example, we write down for sodium. Sodium is 2311 for the sake of example. These are the nucleon numbers, because they contain proton number and neutron number, or the number of protons and neutrons collectively. And these represent the number of protons only, right? So if I wanted to calculate the number of protons, then they will be 11, direct, straightforward. If neutrons are supposed to be calculated, then you're supposed to subtract these two numbers. Why? Because protons are represented over here and they're also a part of this number. So if I want to find out neutrons, I just have to subtract this number from this one. So 23 minus 11 gives me an answer of 12, right? So this has 12 neutrons and 11 protons. And if this would have been a neutral atom, then of course its number of electrons would also have been equal to the number of protons, right? So we also understand this in terms of syllabus as well. Then he says we need to understand the term of isotopes. We understand what is an isotope. Again, from basic chemistry, atoms of the same element. Remember, it needs to be same element for comparison. So for example, if we have chlorine, then we have a chlorine 35, we have a chlorine 37, right? So these are both isotopes of chlorine, right? And I think that the number is 17 probably, but you can see that up in periodic table as well. So they have same number of protons protons are same, but the number of neutrons are different, right? They will have different number of neutrons. And how do we know that? We can just simply subtract them. 35 minus 17 and 37 minus 17 will be a different answer. Although they have the same protons, but they will have different neutrons. So we understand that term as well in terms of physics. We understand this notation as well. AXZ, this is how we have started with the sodium at least. So this is known as nuclide notation. In terms of physics, the technical term for this is nuclide notation. So this is 2311. This is your nucleon number, right? This is represented with letter A, and this is your proton number written with letter Z. Okay, so question number 6 or part number 6 says charge and nuclear number conserved during a nuclear process. Basically, they want to make sure that you understand that during a nuclear decay process of alpha, beta, or gamma, everything is conserved. So let's try to observe the decay equations. Now, decay equations work simple in terms of simple mathematics problems. First, we're going to look at gamma decay because that's the most simplest one. Gamma is actually 0, 0. So if, let's say, uranium 235, 92 were to decay releasing a gamma radiation, so gamma will be part of the products as it is, and uranium 235 will come out as it is as well. But if, for example, because nothing is being subtracted over here, so that's what he means by this term in the syllabus, that the nucleon number and charges are conserved. So based on this idea, if we were to deal with an alpha decay process, then alpha is 4,2. This is supposed to be a part of your memory. You're supposed to memorize this. And let's say we are taking uranium again for this example. So uranium 235, 92 decays to become something else. We are not interested, but releases an alpha particle. And these are the things that are required to fill in, right? So because we know and we remembered that alpha is 4,2, we complete this part of the system, but we are still left with X. So for the upper part, we can make a separate equation, and for the lower part, we can make a separate equation, right? So simple algebraically, left-hand side should be equal to right-hand side. This is what you mean by charge conservation and mass conservation. So this would have been 235 equals to X plus 4. So X would have been equal to 231. So this number would be 231, which if you add with 4 again becomes 235 again. So this is the simple logic behind it. Similarly over here, this is going to be 90 because if I add 90 with 2, this will become 92. Or if you want to look at it from an equation perspective, this would have been 92 is equal to, this arrow is being treated as equal to plus X plus 2. So if you take 2 over there, X becomes 90. Similarly, let's move on to beta decay. Now, I will not go into details of beta decay right now because that is going to be a part of the next part of this lesson. So just bear with me. I will discuss this radiation or this decay in detail. But anyways, for the sake of simplicity, I'm going to simply write down a simple equation so that whoever is just trying to understand decay equations can understand how to solve them. So if your uranium decays with beta decay, and of course we're dealing with beta negative decay, something new will be formed, and we are not interested what is the name of that element, but we are interested in the charge conservation. So for beta, we need to remember that this is beta 0 minus 1, right? So based on this idea, we can see that nothing will be subtracted from this because beta has a 0 over there from maths perspective. So this is going to be 235 as it is, no issues at all, right? But what about the lower part? So for the lower part, we need to make this as an equation. So we have 92 equals to X plus minus 1. This is a negative sign, so this will be a negative 1. But when you take this over there, this becomes addition. So this becomes X equals to 93. So over here, you're going to add 93. This is against intuition. You haven't thought about it. It doesn't appeal to the common sense, but yes, this number is going to increase. And why does this increase? What's actually happening at the back end? For that, you'll have to go forward to the part of the video where I'm going to discuss beta decay precisely. That's an entirely different topic entirely, right? So I'm not going to get into the details at this point. Anyways, all right. So then we have composition of alpha, beta, and gamma. What are they going to look like and what they actually do? So, okay, so this is the part of the syllabus. He says represent alpha, beta, and gamma, and in the form of this equation, we must be able to form the decay equation. This is what we've learned so far, right? Now, this part from 8, 9, and 10, this is actually going to be dealt in the next section as beta decay. So I'm not going to get into that right now. I will be getting into that later. Point number 7 is the charges and properties of alpha, beta, and gamma. We're going to get to that later. We're going to get to that right now as well. And then we have to learn about atomic mass unit. We will get to that right now as well. So let's look at the common properties of alpha, beta, and gamma. So this is actually an MCQ. So I've taken the MCQ as a part of your notes as well. Again, go back to O levels, memorize everything again. This is exactly this chapter is on top of O levels. You need to have those basics strong. Anyways, we have charge, mass, and speed given to us. So X is a particle that has no charge, that has no mass, but is traveling at the speed of light. So to my understanding, this is gamma radiation, precisely. Okay. Then we have a negative charge, a mass that is less than proton or neutron, and is traveling almost close to the speed of light. This looks to me as a beta particle. Similarly, Z is a particle that has +2 charge, and that looks like alpha 42. So it has 4 times the atomic mass unit and +2 charge because of 2 protons, and is traveling much slower than the speed of light. So this looks like alpha. So our answer will be Z is supposed to be alpha. So this is going to be our answer as option C. Okay, let's move on to the next part. This is actually going to deal with the decay equations, which we've already learned, right? So he says that we have this element and it decays down to become something X. He says, what is X? Let's do the algebra. So this is 4, 2, this is 4, 2, and beta is 0, minus 1. What could have happened to this 217? Let's try to observe that, right? Let's pull up a calculator and see what's happening. So we have 217 and subtracting 2 alpha. So this is 217 minus 4, and beta is 0. So subtracting that becomes nothing. So this is 209. So X should be 209, right? So I can go straight away towards option C, but let's calculate for the rest of them. It starts with 85. So 85 minus 2 plus 1. Be careful about this one. So this will be 85 minus 2 plus 1. This will become 82, which is option C precisely. Okay, so we have helped, we've taken the help from the decay equation aspect of the topics that we've learned, or we should at least learn. Okay, next is we have radon decaying to become something like this one. He says we don't know how many alphas and how many betas are going to decay to make this. So let's figure out that. So we have Rn as 222 and 86 finally becoming something like this. So this is going to be 214 and this is 83. So first let's calculate, because we know that even if there is beta decay, we know that beta is 0 minus 1. It will not disturb the upper part of this equation at least. So let's figure out how many alpha may have been ejected from the system. So 222 minus 214 gives us 8. And since alpha as 42, in the upper side there is 4, that means that there needs to be at least 2 alpha decays from this nucleus. So this is going to be option B or D at least. Moving on to the next part, if 2 alphas have been rejected or have been ejected from this, then most definitely this is going to be minus 2 at least 2 times. So this will become 82. But we have 83. That means that something was added and it can only be done in beta decay, right? We have seen that in decay equation as well, that when you do that, actually 1 proton number gets added into this. So this is going to be at least 1 beta decay. The most common answer is going to be option B. Okay, so then we have the again leading with the common properties of alpha, beta, and gamma. This is the part number 7. We need to understand how they're deflected in electric field and magnetic field. So let's go to that. So first we have deflection in the magnetic field. Sorry, electric field. This is going to be electric field. Let me erase this for you. So this is primarily electric field. So notice what's happening with alpha, beta, and gamma. You see, gamma has no charge, that's why it's passing straight through, undeviated, undeflected. Beta has a negative charge, that's why it's moving towards the positive plate. And alpha has a positive charge, it is moving towards the negative plate. But you might see that there's one clean distinction between them, which is not because of the diagrams issue. This is actually a legit part of this understanding as well. You will see that beta moves towards the positive plate much quickly as compared to alpha moving towards the negative plate. Why is that so? This difference in deflection actually shows their mass. Beta has a very small mass in comparison to alpha, or we can say that alpha is very heavy in comparison to beta. So alpha responds to the electric field and deviates much later in comparison to beta because alpha has a high mass. So its inertia is higher. So its electric field or electric force on the particle, on both of them is same. But because of their different masses, they're experiencing different accelerations. That's why alpha comes to the plate later and beta goes to the plate much quicker. Because it's lighter, it will respond to the force much quicker. So this is an important difference between them. This is a part of an MCQ. Moving towards the magnetic field, right? To understand how they're going to move through the magnetic field, we need to understand we need to recall Fleming's left-hand rule. And we have also known that rule as well. Left-hand rule, right? So we understand that the first finger represents the magnetic field, the second finger represents the direction of current, the third thumb represents the direction of force. Now, since alpha is a positive charge and the Fleming's left-hand rule is in accordance with the direction of conventional current, so we will take this direction of current to be the positive side of the current, and this will be the direction of current for at least for the left-hand rule. Now let's see how we're going to arrange our hands according to the first case, the alpha. Now gamma passes straight through, we understand, because it has no charge, no current, no mass. It passes straight through the magnetic field as well, undeviated. But let's see how alpha particle is going to move. So how are we going to arrange the hand for the alpha particle? Now this is the first example. This is for the alpha particle, how you're going to place this hand in this example. You see, first finger is pointing away from you. Why? Because this magnetic field is actually into the page. So this finger is in accordance to that. Second, this is what the magnetic field is right now. Okay, so based on this, you can arrange your hand for that. Second finger is representing the direction of current, which is the direction of the alpha particle moving towards this side, right? So this is the direction of the alpha particle's movement. Once you've done that, you will notice that your left hand will automatically point the thumb in the upward direction, which is where this alpha particle is experiencing a force towards that direction. I hope that we understand how we can apply that. Similarly, if you were to find out for the beta, generally what I tell my students is solve beta thinking that is alpha, and at the end of the question, reverse your answer. But if you want to truly understand how beta is going to work out, then we need to understand that beta is a negative particle and we are dealing with conventional current. So we have to assume, even if it is moving towards the direction, we have to assume the direction of current in the opposite direction as of alpha or as of a positive charge. So notice that you'll have to rotate your wrist, rotate the same wrist towards clockwise direction, and you will eventually go to this orientation position of the hand. Okay. Now, what's happening at this point? You can notice that still right now, the first finger is still pointing into the page in accordance with this cross. It is still pointing towards the board, right? Where you can see the cross right now. The second finger is in the opposite direction of the beta particle. So I'm pointing it towards the left side, opposing the direction of the beta particle, right? Okay. And when you do that, you open up your thumb, it opens up downwards, and you can see that this is moving downwards. Alternatively, again, I repeat, you could have done this question thinking that it's an alpha particle. Then the orientation of the hand would have looked like this, which is much easier to replicate as opposed to this one. So at the end of the question, if it is pointing upwards, now since you know that it's beta, you will reverse your answer that is pointing downwards. Again, your choice. If you're comfortable with both gestures, it's up to you. So we understand what common properties of alpha, beta, and gamma are as well. We understand the decay equations as well. And let's try to understand the atomic mass unit. What is that? So we have AMU, or atomic mass unit. Basically, this concept stems from the topic of mass defect, which is also a part of A levels or A2 as well. So I'm going to give you a brief description what that is. So basically what they discovered was that if you, let's say, take a nucleus of helium, let's say, that has 2 protons, 2 neutrons, and you take just 2 protons and 2 neutrons separately, when they are inside the nucleus, when they're a part of the nucleus, their mass tends to be smaller as compared to when they are outside, which is peculiar because it shouldn't be different. They should have been equal at best, or at least they shouldn't be different from each other. But why is that so? They figured out that when you provide energy to this nucleus to break it apart so that its constituents or its nucleons inside the nucleus can be seen, this energy is known as binding energy. So we needed to provide this much energy. It's just a name, of course. We needed to provide this much amount of energy to break it apart. Once we break them apart, their mass suddenly appears to increase. So this is where you come up, this is where Einstein came up with the equation of E equals to mc square, that this mass is actually the mass defect, the difference of mass between the constituents or the nucleons and when they were inside the nucleus. This is actually delta M, or mass defect. Let's call this M1, let's call this M2. So this became M2 minus M1, the change in mass multiplied by c square, is the energy that you provided to break the nucleus apart. It is now visible, or it is now accountable in terms of its higher mass. So if you provided high energy to break it apart, it will show up as mass. But that is why you actually come up with this law of conservation at atomic level, at a nuclear level, that energy and mass are always conserved. And you will see this answer many times in marking theme of P2 as well. But it doesn't make any sense. Now I hope that it makes sense, that what they're trying to say, that energy is mass and mass is energy, or they both are interchangeable to each other. Now, where does this AMU take into place? You see, when they are outside, a proton measures 1.67 up to many decimal places into 10 to the minus 27 kg, and a neutron weighs 1.6 or measures 1.68 into 10 to the minus 27 kg. The neutron is slightly heavier than the proton, right? So now this is when they are outside, but what's their mass when they're inside? When they're inside, protons and neutrons, each of them have the same mass, or you can say it is believed that they have the same mass, because what we did was we measured the whole atom and we just simply divided that mass with 4, because there are 2 protons, 2 neutrons. And that number comes out as 1.66 into 10 to the minus 27 kg. You can see that in their numbers as well, that previously proton, neutron have a mass of 1.66. After they're outside the nucleus, one becomes 167 and one becomes 168. The mass is increased slightly, which is peculiar, which is an odd behavior. It shouldn't happen this way, but it does. We have observed it. That's why we have the equation E equals to mc square. So that is what AMU is. AMU is atomic mass unit, A 1.66 into 10 to the minus 27. Why does he want you to be familiar with this? Because he's going to ask you to predict the mass of a nucleus. For example, if it says that magnesium is 2411, what is the mass of magnesium, or what is the probable mass of magnesium? You see, we have 24 protons and neutrons, right? So simply 24 multiplied by 1.66 into 10 to the minus 27 kg. So whatever answer in the options is given, this will be the answer of that system. And to be familiar with the mass concept of mass defect, the difference where the equation comes from, and what is AMU. That's what we are required for this part of the course. So we understand this AMU as well, the atomic mass unit as well. We understand this as well. What we're left with is 8, 9, and 10. So they will be covered in the next part, right? So we are just going to encounter that. Now, one more thing about nuclear decay is that nuclear decay of alpha, beta, and gamma has 2 concepts. That it is sometimes spontaneous, it is sometimes random. Random purely deals with unpredictability. What sort of unpredictability are we looking at? We're looking at the unpredictability of direction. Where is it going to go? If alpha and beta are being radiated, in which direction they will go? We don't know. Which atom will decay? We don't know, right? And when an atom is going to decay, we don't know. If you're observing, let's say, an atom in a sample of 10 grams or 20 grams of uranium, we probably may be looking at it, but we don't know which one is going to decay. So this sense of unpredictability is known as the random nature of radioactive decay. And this is usually seen, or how did we know that this is actually happening? This is seen as fluctuations on the GM tube reading, Geiger-Müller counter. The fluctuations are seen something like this. The decay is there, but the reading is sometimes higher, sometimes lower, sometimes higher, sometimes lower. It's not a steady value. So these fluctuations in the GM tube value is actually the guarantee of radioactive decay being random. The other concept is about spontaneous. So what is spontaneous? So it says that radioactive emission is unaffected by environmental factors. It could be that you're adding an acid, or you're adding a base, or you're adding a chemical to increase or decrease the rate of reaction or the rate of decay process. It will not be affected. Similarly, by adding pressure or placing it close to an explosive, probably that may increase or decrease the rate of decay. No, it does not. Probably providing it with a large amount of heat, because these things what we observed in chemistry. If you add acid and base, the reaction becomes violent. If you add pressure to the gaseous situations, according to the Lee-Chatelier principle in chemistry, the rate of reaction changes. And for example, if you heat up the chemicals, the kinetic energy increases, they collide with each other, the activation energy is reached or breached much more quickly. It is easy to do, so the rate of reaction increases. So these things work in chemical reactions, but they don't work in nuclear reactions. That's why this is referred to as being spontaneous. It's happening on its own. We have no control over it. So spontaneous nature of decay. The decay is affected by pressure. No, it's not affected by pressure. Yes, this is being spontaneous. Is not affected. Yes, the decay is not affected by temperature. Yes, the decay radiation is received at the counter fluctuate. No, this is the randomness. So random is what causes the fluctuation in the reading. Now let's go to this side. Decay is not, this is being spontaneous. At the counter fluctuate. Yes, this is being random. This is being random. Decay affected by pressure. No, this is being spontaneous. Pressure spontaneous. So the two things that are matching in both columns is option B, right? Okay, so we understand this point as well. Now we go back to the syllabus. So now 8, 9, and 10 about beta decay will be covered in the next part. Now let's move to the next part. So first we need to map this whole topic. This topic from now onwards is purely 100% based on your memory. You have to memorize each and every bit of this topic that I'm going to teach you right now. Okay, so let's move on with this topic, and we will cover the beta decay in this because we can see beta positive and negative decay as a part of this lesson as well. Okay, let's move on to this one. He says we need to understand that there are elementary particles. Let's move on to the next part of this. Okay, so I'm going to make this into a two-part series. The first part has already been covered, right? So the next part will be uploaded in the second part, or as a second part of this chapter. See you in that video.